I think you mean there's still like four more? Okay. Yeah.
There's matrices. I love matrices.
You will love that. All right, let's talk about like lines, but this time today, let's talk about them in 3 dimensions. This will be fun. Here's your review from the previous lesson. I just copied and pasted this from the previous slide. You do not need to write this down if you have very good notes. You already have this there. It's just the same diagram, copy paste. Okay. The only thing we want to add, the big takeaway on this slide is, and I think I gave foreshadowing of this the other day when we were doing lines, is that all we do for a 3D line is add another component. Right? It's still the same equation though. It's still position vector plus parameter times direction vector are the words I've been using. Position vector plus t times direction vector. It's just we have a third component. We have z, we have, okay, everything's fine. Nothing to see here. And keep in mind that this is nice and very easy. It's almost like you're like yawning. You're like, okay, sounds like we're done. But think about how hard it would be to generalize another notion of a line. Give another equation of the line that you know in 2 dimensions. How would you extend that to the 3rd dimension? It'd be very hard or not meaningful or impossible to do that. Whereas with this notion of the line, this vector equation of the line in 2 dimensions, it is really just child's play to extend it to the 3rd dimension. Just add another component. So this is great. I hope you see, but this is just wonderful. Some of you are taking very, very careful notes on this slide. Wonderful, good job. But just keep in mind, the only takeaway from this slide is add another component to what we've been doing before. So to prove that this really is easy, try it now with 2 points. I'll give you 2 points. You come up with the equation of the line between these 2 points, and also, just for fun, determine the coordinates halfway between them.
So we're not doing like it actually like okay.
Yeah, come up with the vector and parametric equations, right? So x, y, z equals direction. Come up with the vector equation that we just wrote down up there first, right? Position vector plus t times direction vector. We'll give everyone 2 minutes again, and we'll call on someone randomly.
Oh, never mind.
T is the parameter.
It's the variable. It stays visible. I remember that. Yeah, I didn't think about that.
So
What? Wait, I don't understand how you're supposed to incorporate those.
T is just a free variable, right? That's the parameter. You don't have to have a T in it. I mean, you have the T. It's just a T.
Oh, okay.
Just T.
Oh, so I got -4, 3, 4, and then plus t times 4 is 2, and then oh wait, probably not 4. -6. Wait, what?
-2 minus -4. So 2. The other ones I think I like though. What was that? What was that? 2.
2, 2, and then 1.
Everyone agree with those other values? Okay. Good. There's the vector equation. And do you also want to give the parametric equations? What would they be then? X equals, y equals, z equals. What would those be then? If you actually start adding this stuff together, what do you get? You have it, Kim? The parametric equation. Yeah, so it'll be, right, I mean, just start combining these here.
Oh, okay. Yeah, so it would be -2 and then 5 and then 5.
Well, I guess by combine them I mean
Oh, wait, right.
via
Yeah.
scalar multiplication and then vector addition.
Yeah. Okay, never mind. So it would be, so it would be 2t minus 4.
Yeah, 2t minus 4 and then t plus 4. You guys see what we're doing here? Do you agree that when you add them, do you get those things? This equals this. Do you agree? Multiply the t in. Yes? Jeff? Jeff? So t is a free variable. If t is 0, we get this point. If this is a line we're talking about. If t is 1, where are we at?
Wow, I'm so genius.
We're gonna illuminate it a little more in just a second too. This problem, I'll tell you. Let's finish it off real quick though. Go ahead, Kaylin. What's how do we get the midpoint?
Oh, you add the,
Can we use the equation of the line somehow to get the midpoint?
Oh, I get it.
Well, that will work. That's true. If t is 0, let's remind ourselves what point is this where are we on the line? A. If t is 1, where are we? B. Do you see it? If t is 1, we're just adding the vectors back together and we get b. Where are we if t is, well, what t would we like? In order to be halfway between them, we want not one whole copy of the vector from A to B. We only want a scalar multiple of that, 1/2 of that vector's length. Yeah, so if t is 1/2, what do we get? Is the point, right? Good. And then just to illuminate this a little more, I just coded this up in GeoGebra here. And I want to make sure you're seeing this in 3 dimensions. Are you ready? Okay, so here we've got the 2 vectors, the 2 points we started with, A and B up here. Do you see them? Floating out there in space. And so we've got in blue our position vector. And then we built a vector from A to B, the points from A to B. And the way that this is visualized is down here. Does that look like the vector from A to B? It's just positioned at the origin. But is that the right direction from A to B? This red vector down here should be pointing with the same magnitude and direction as from A to B, right, if you were to translate it up there. So, now, the gray vector is a vector that is one copy of, this is A plus C, is the, right now, I just have that plus, t equals 1 here. So just like we said, it will point to B. If t is 0, where does it point to? What do we say? A. And if t is 1/2, we're right there, halfway between. If t is 2, where are we? We're at a point twice as far away from A as B is. T is -1. We're over here. And if t is other things, what is it pointing to? If t is other things, what is it pointing to? Points along the line, right, that we're talking about, right? This is the line we're speaking of, isn't it? Can you see it clearly now? This is the very problem we were just doing, and now you can see it a little better. So there's A and B. This is the direction vector if you were to move it up here. And as you see the gray, all I'm having it do right now is this gray vector is various t values, right? Like we said, if t is 0, we're pointing to A. If t is 1, we're pointing to B. If t is 2, we're right there. I don't know if that helps, but I like to see it.
I don't get it. How different it would be?
So different t values produce different points along the line, as you can see.
You get credit for nothing.
All right, so let's move along here. If we have 0, -2, 3, we want the equation of a line containing that point. So already I'm feeling like I want to make one disclaimer too about the last problem. Keep in mind that 2, 2, 1 is a great direction vector, but so is 4, 4, 2, or any direction vector that would have pointed in the right direction would have worked for us. And furthermore, any position vector would have worked. So this one, we want to say something very general here. When you're coming up with the equation of a line, there are many correct answers. I think most of us probably would have come up with this one, maybe. But just keep in mind that this here could be any point on the line. This here can be any vector that points along the line. So that means scalar multiples. Any scalar multiple of this vector will do. All you need is a vector that does the job. So let's keep that in mind. Certainly we have a point on the line here, so it makes sense to use it for our position vector maybe. That's fine. You're welcome to do that. But we need a direction vector. Now it says something interesting. It says the vector perpendicular, we need the line to be perpendicular to the xz plane. Now let's take some visualization. X-axis, y-axis, z-axis is my head. Okay, so my body is the z-axis. Okay, so where is the xz plane? That is the plane containing the x and z axis. That's over here, right? The plane that contains both my body and my right arm. Right. So now the next question is, can you come up with a vector for me, please, that is perpendicular? Any vector at all will do. That's perpendicular to the xz plane. Don't think too hard. What vector is perpendicular to the xz plane? What is it? Yeah, any vector that points in the y direction, right, along the y-axis. So name one. Name one. 0, 1, 0, right? Or 0, comma anything, comma 0 would do the job actually, right? So I think we're done with this problem. And by the way, you can probably name a point on this line too. One of the other points on this line would be 0, -2, 0. Right, all the other points that have the same, sorry, did I say that right? No, I'm sorry, 0, anything 3. So actually, so this number could be changed here is the point, right, as we move along the line. So actually, yeah, you could just say the equation of this line is x equals 0, y equals is free, and z equals 0, right? Or z equals 3, rather. Let's visualize this here. All right, so this time I've got here the point 0, -2, 3, and then the vector that you just told me, 0, 1, 0. Yeah? In pink there. Do you see the vector 0, 1, 0 pointing directly in the y direction? Is that perpendicular? Does it look like to the xz plane? Let me reveal the xz plane so you can see. Does that look perpendicular to the xz plane?
No.
Yes, it is. The pink vector is definitely.
Okay, so the pink thing is on the green line.
Yeah, it's hard to see there, but there it is. All right, and then, of course, the line we're talking about that we want to speak about is the line that goes through this point and follows this direction vector. So you can imagine adding copies of this vector to this vector. That would put us there, or 2 copies would put us there. All along, back and forth, parallel to that little pink vector, we would get this line. You see, always parallel to the pink vector down there, pointing along that line. So there's the line the line we just came up with. That's a little disorienting. I think that does the job, doesn't it? Someone explain why these are parallel. Turn to your neighbor, everyone, right now. You don't have to, you can write it down too if you want, but look at it for a second, and then turn to your neighbor at your table and tell them why you think these are in fact parallel.
Oh, because they're scalar and multiple. But they're attached to C.
All right, what's the answer?
Because the thing that's attached to T, the coefficient of T, but not really the coefficient, are scalar multiples.
Yeah, what did we call that?
Direction.
Okay.
I didn't know that until Kaylin said it.
All right, but this is the plot of those two lines. I don't have anything else to say about it. Just that, do you notice that they're parallel? Yeah, they are. Okay. Moving on. Okay. That's a little fast. I apologize. But there they are in 3 dimensions, 2 parallel lines. Yay. Okay. Let's first digest what we're looking at on this slide. Are those really the equations of 2 different lines? First study, it'd be like, I'm not used to that way of writing it, but let's just look at the first one, for example. Is that the equation of the line? Just get to the place where you agree that it is. It's actually kind of a nice way to see it, actually. X is t minus 8, y is 2t minus 8, and z is negative 2t plus 5. You can get that back into vector form if you prefer that. And we got another line too. And the question here is, do the lines intersect? Now we want to make sure we stop and understand what we even mean for the lines to intersect in this context. There would be one very, very high demand. Imagine two, and this is not what we mean. Imagine 2 flies were flying along 2 different paths in this room, along lines. Yeah? That's the situation we're kind of in. The demand that that these intersect is not the demand that the 2 flies hit each other, right? Because that would be the demand that not only do their paths cross, but that they hit each other at the same moment, right? That not only do the lines contain the same point, but that the t value for both lines agrees at that point. That's a very high demand. It's us demanding that the flies actually hit each other. That's a higher demand than what we want. We just want, when we're talking about the intersection here, we just want to know, do their paths cross? That is, if they were to have left contrails, did they intersect at a place? Were they at any time at the same location? Did they ever occupy the same space in the room at the same, but not necessarily at the same time? So because of that, I'm going to suggest that we do one small thing. So first of all, I think you maybe would prefer to rewrite the first line this way. Would you agree? There's the first line, written in a way that you might like better. Yeah. The second line I'm going to propose, though, because of the whole thing I just said about the fly, that is, we don't demand that the t value for both lines be the same at this point of the intersection. I'm actually going to change the second parameter in this line, in the second line, to be a different letter, just so we don't get confused. There's 2 different t's here. So let's just name it something else. How about s? So we'll... I just like S because it's near T in the alphabet, but you can do whatever you like. Okay. All right, I just want to make sure everyone's clear on what I did, where I got all those numbers, and like why I did that based on a fly discussion. Is that okay? All right, now we can commence thinking about what it would mean to find the intersection. I think it makes sense to think about the intersection. We'll move forward, assuming that there isn't an intersection. We'll see if we run into trouble here. It would, by intersection, we mean, is there a place where the x coordinate is the same on both lines, and the y and the z coordinate are the same, right? Is there ever an s value and a t value that produce the 3 same values here, right? So just to put a finer point on it, we're looking for a time when t minus 8 is equal to 2s minus 1. Do you see where I got that equation? Okay, and 2t minus 6 is equal to s plus 2. All right, and actually I'm not going to go and write down the z equation yet because that looks like that's all I need, right? Friends, to get s and t, 2 equations, 2 unknowns. Let's solve. Go ahead. That's a little system of equations, right? Figure out what t and s are that would make that system true. Use whatever method you like. See if you can beat me to it.
Nope.
When you get it, just to verify that I got it too. You get the same answer as I did. Of course, we're not done. Did you get? I used substitution with one of them. You might have done something slightly different. I don't know.
No, okay, so if you want 15.
All right, so what's x, y, and z, though? That's really the question. What's x, what's y, and what's z? What's x first? How do we find it? Well, x is given by this equation here. T is 3, so what's s? Or what's x? Looks like -5. Wait, before I get too carried away here, is that also what this says? -2? If s is -2. Yeah, so I think we're okay. Things are going well. What about this one here? What do we get for y? Make sure they both agree. Put in t here and s there. What do you get? Do you get 0 from both of them? All right, now that is actually not a huge surprise that we got agreement for the x and the y coordinate. Why? Well, because we solved the system, right? So of course, if you don't get that happening, then you solved the system wrong, right? That should always happen. The big test is what's now coming up. Notice that we haven't ever talked about the z equations. So if they don't intersect, this is how it feels. You get x being the same, y being the same, and then z being different. So this is the big question. Do you get the same thing for z? Oh, what is it? It's so exciting. We do have an intersection, you guys. And there it is, right? Some of you aren't as excited as I thought you would be. Here's the. Here's the. Well, that's not it. Okay. I thought I had one here somewhere. Come on now. How do I get my other? I think it's example 4 actually. Let me see it here. Example 4. Maybe this one here? I think this one. All right, there we go. 5, 0, -1. You can't see it, but there they are, intersecting just as we wanted them to, right there. So, I don't know. This one maybe not as, it's not very climactic, but I'll give you one more.
What?
So give that one a try just for practice. We're coming up fast on the end of the period here, so see if you can come up with an answer in the next 2 minutes. And but I think you're well prepared for homework 7 tonight, which is a worksheet I'll be passing out momentarily. Aren't you all about the worksheets?
Yes, I
Okay.
like them better.
Yeah, do that on the.
Then it's easier to do on the way to class. No, I'm kidding. I'm kidding. I'm kidding.
I can't believe there are people who wait till the last minute to do a worksheet.
Worksheet sales.
I've never heard of microreaders.
Worksheet sales.
I think we have one extra Mr. Chase.
Yeah, but it's
Never
for
mind.
you.
I didn't think you'd notice.
Wow, you really wanted me to get a 0 out of 2 tomorrow. You're a fake friend. No. Let's do it all the way. It's so no, I'm kidding. Oh, it's still working.
How do you put that?
Cause like, why?
No, we're following the ladder. It's so close. I'll check dog. Dog.
Mr. Chase, these videos are priceless. We're famous. He's got to sell them for like $1 billion.
Maybe it does, maybe.
Already.
Or black. It doesn't work.
What are you talking about? I'm going to win a Nobel Prize for my jacket.
Cause like,
And then I'll be famous. You found out my jacket
Yes.
experience.